In 2019, humanity captured a photograph of something that, by definition, cannot be photographed: a black hole. Not light bending around it, not an artist's impression, the actual shadow of a hole in the universe, 93 million miles across. But here's the question nobody could really answer that day. What is actually inside it? A black hole isn't really a hole in the sense of a hole in the ground. It's what happens when enough mass gets crushed into a small enough space that space-time itself folds in on it. Einstein's equations describe gravity not as a force, but as curvature. Mass tells space-time how to bend, and space-time tells mass how to move. Around a black hole, that curve becomes so extreme it closes in on itself. That boundary is called the event horizon, the point of no return. It's not a physical surface. There's nothing to touch. It's simply the line where the escape velocity needed to get back out exceeds the speed of light. Cross it, and every path forward, every possible direction you could travel, points deeper in. Not because something is pulling you, because space itself is falling, and you're falling with it. From the outside, we can already see plenty. Superheated gas spirals around the horizon at close to the speed of light, glowing across the entire electromagnetic spectrum before it disappears. That's most of what telescopes like the Event Horizon Telescope actually detect. Not the black hole itself, but the last light emitted by matter right before it vanishes. Say you fell in feet first. Near a small black hole, the gravity pulling on your feet would be dramatically stronger than the gravity pulling on your head. That difference stretches you, a real effect physicists actually call spaghettification. Around a supermassive black hole, though, the horizon is so large that the stretching is gentler, and you could cross it without immediately feeling a thing. Time gets strange, too. To someone watching from far away, you'd appear to slow down and freeze right at the horizon, your image redshifting into darkness, never quite seeming to cross. But from your own perspective, you'd fall straight through in an ordinary instant. No flash, no wall, just crossing an invisible line. And then, according to Einstein's equations, at the very center is a singularity, a point where density becomes infinite and the equations simply stop giving sensible answers. This is where general relativity, the theory that predicts black holes exist in the first place, admits it doesn't know what happens next. Most physicists don't think infinite density is real. They think it's a sign we're missing a deeper theory, one that unites gravity with quantum mechanics. That missing theory matters because black holes create a real paradox. Quantum mechanics says information can never truly be destroyed. But if you fall into a black hole, and the black hole eventually evaporates through what's called Hawking radiation, where does your information go? Stephen Hawking himself spent decades wrestling with this. It's still not fully resolved. Some solutions to Einstein's equations even allow for something stranger: a bridge connecting the black hole to somewhere else entirely, a wormhole. It's mathematically valid, it's never been observed, and most physicists think it would collapse instantly. But it hasn't been ruled out. So what's really inside? The honest answer is, we don't fully know. Everything past the event horizon is, by definition, cut off from observation. We can calculate, we can theorize, we cannot see. And maybe that's the most honest thing science can say about the strangest objects in the universe. If you want to go deeper into questions like this every week, subscribe, because this is the big question.